All right, share the screen. So, this is yet another talk kind of influenced by Cubism and the Cubist kind of formulation of quantum mechanics. Although we won't be kind of talking about the philosophy of it specifically, just some of the cool mathematical objects that come up. And so most of this, what I'll be talking about today, comes out of like two papers, which are both worth reading. One is this one, Symmetric Informationally Complete Quantum Measurements, from way back in 2003. Short paper. And then mainly this one from 2006, Tight Informationally Complete Quantum Measurements. And so the general theme is we'll be talking about quantum measurements or generalized quantum measurements that are, say, like optimal for doing tomography or state reconstruction. And a lot of what I do is sort of summarizing this paper. I don't include like all the proofs. As I say, I have a little link at the end. So if you're curious about, some more of the details, it'll be there. So first thing is we're gonna talk about spherical T designs, which I like because, as you guys know, I love spheres and constellations on spheres. And this is like yet another use of them, completely unrelated to anything having to do with the Majorana stuff from way back when.
Matt, can you make it bigger?
Oh, yeah, for
sure. Difficulties reading it. Much better, thank you.
Nice. All right, so spherical T designs are useful in doing like numerical integration. So the idea is, suppose you have some polynomial that you want to integrate over some space. With a spherical T design, instead, you can just take a finite sum of the values of the polynomial evaluated at some specially chosen points, and you'll get the same answer. So a spherical T design is a set of n normalized vectors such that the average value of any Tth order homogeneous polynomial over the set is equal to the average over all normalized vectors. So, the idea of it being a T design is that you can use it to integrate polynomials up to order T. So, you can't just, integrate for free in a way. There's like this limitation. So for example, if you wanted to integrate, you were integrating like a function over like the two sphere, just like the normal everyday sphere in 3 dimensions. And you had some Tth order polynomial, call it f of t. And you have n points in your design. Then you'll find that, here's the integral of the polynomial over the sphere. It's weighted by like the surface area, the average value. And that's equal to the polynomial evaluated just at these special design points over the number of design points. So an average again. So we'll see that in what follows, that a set of T design vectors have the property that they minimize the Tth order frame potential. Frame potential, you'll see that there's a connection to frame theory, as we talked about last time.
Matt, where does n come from? What is the value of n?
Yes, n is the number of vectors in the design.
Is it related to t?
Well, there is like a bound on like the number of points n that you'll need for a given t and dimension. But no, I mean, they can vary. So the t has to do with the order of polynomials that you can integrate in this way. And n is like the number of points on the sphere that you're evaluating a polynomial at.
When I see a polynomial, how do I know how big n should be?
Yeah, it's a great question. Yeah, down here I have a little thing. Where is it?
Okay, if you will get to it, that's okay.
Yeah.
So
Wait,
we
well,
get it in proper time, that's fine. I just wanted to make sure that it is not an arbitrary number.
yeah, it's not totally arbitrary. Yeah, here. Now, okay, well, this is for a slightly more general concept, but here's one bound, like n has to be great, at least this much. D is the dimension, T is the design. I don't know if this formula exactly applies to spherical T designs. Wait, let me see. Consult this book right here. That's why I got it. Page 116. Okay, less easy to find than I thought. Yeah, there. Yes, you need like a minimum number of design points.
Okay, why don't you just continue?
Yeah.
Sorry for interrupting.
No, it's fine. So it turns out that a set of T design vectors, by the way, part of the problem is, I should mention, like if you go to like look up some of this stuff, in this world, there's like a weird profusion of like terminology. There's like spherical design. Sometimes people call these spherical half designs. There's like tight designs. We'll generalize the concept to like complex projective designs, and it's tough to keep everything straight sometimes. So yeah, I forget the exact bound on n in this exact case. So we'll see that a set of T design vectors have the property that they minimize the Tth order frame potential. And, but the name suggests there's a connection to frame theory. So, you just kind of go over the vectors, take these inner products, absolute value squared times T, 2 times T. So,
one moment, those vectors, where do they come from? Psi I and psi j?
Yeah, so like in this case, they're just like,
Okay, oh, those are the points. Okay.
Yeah. So, in Cartesian coordinates, there'll be like some x, y, z's.
Okay.
And eventually there'll be quantum states in like what follows. So hence the notation.
Okay.
So just from what I just said here, I didn't prove this, but if we minimize this quantity, we'll find a spherical T design. So here is a little code that does that. This is kind of interesting. Like, if you do any Python programming, it's definitely worth knowing about JAX, which allows you to compile your code like on the fly, as well as take derivatives of your code in a way that like respects linear algebra and all sorts of great stuff. And so what we do here is we define the frame potential for some T. We find its like derivative because we want to, fall down the gradient, try to like minimize the frame potential. We have here, we want the vectors to be normalized. So this imposes a norm constraint. We want all the vectors to have as close to unit norm as possible. And then we use SciPy's optimize function, or its minimize function, to do a constrained optimization. We want to minimize, starting from just like some random set of vectors, we want to minimize the frame potential under the constraint that the vectors have unit norm. So let's do it. So here we'll find for dimension 3, everyday, 3 space, say 6 vectors that form a 2 design. So it did it. Here's the vectors. The columns of this matrix are the vectors. So then we can check it out. Like, so let's make up some random second order homogeneous polynomial. So, this takes like a little vector, like that's like XYZ as input. And, we're like x squared plus x times y times 6, whatever, z squared plus 5z times x plus y squared or whatever. Homogeneous, recall, means just that all the terms have the same order. So either they're like, in this case, x squared, or 2 of them multiplied together. So another great Python library that's like worth knowing about is QuadPy, which does like numerical integration. And like ironically, they're probably using like designs, like under the hood to do this. In fact, that's sort of what this. Well, I forget exactly what goes on, but you can look at the docs. So we'll get a scheme for integrating over the sphere, and we can check it out. So we can evaluate the polynomial at each of the design vectors, and then divide by the number of design vectors. We get this number. And then we can integrate that same polynomial over the 2 sphere, divide by 4 pi, the surface area. And we get the same number-ish up to, numerical error. We could try to push this further, Here's like the error tolerance.
Wait, Matt. The 6 vectors that you have right now at the bottom of the page.
Yeah.
How did you get those 6 vectors?
So they came out of this little optimization algorithm. So this basically starts with a set of like 6 random vectors, and then it can calculate like the gradient of the frame potential, right? Because we want to minimize this. I didn't show like why this works, but just for now, we got to minimize this to get a t design. So I set t equals 2, so this will be like to the 4th. And I try to, descend down the gradient to try to like kind of update my vectors so that they get closer and closer to minimizing the frame potential under the constraint that they have unit norm.
This is amazing.
Yeah, I mean, yeah, I love it. It's great. Well, that's what, SciPy Optimize is great, very useful. And then this JAX thing is awesome because it like, Python is an interpreted language. And so it's kind of slow sometimes, but this sort of like compiles, your functions down to like, machine code. And it can also really easily take like the Jacobian, or like, AKA like, the derivative of, these like matrix or like vector valued functions and stuff like that. So it makes it very easy to do this, this kind of thing.
What would be interesting for me, at least, is if sometime, that doesn't have to be today, but if sometime you can provide an outline of the proof that this sum gives you the value of the integral.
Yeah, well, I'll be able to flesh it out a little bit more as we go on. Yeah, and I have to say, I've been working through this paper. There's still some stuff about it that I don't quite understand, so we'll come to that. So okay, so it worked-ish, and we can look at the points too. So these are the points that it found. would we know that that was a design just from a two design just from looking at it? I don't know, but there it is. Okay. So what follows now is like very closely adapted from this paper, Symmetric Informationally Complete Quantum Measurements. So, as we talked about, at the last couple meetings where we discussed like frames and stuff, a frame is also like a design, a collection of n vectors. And they form a frame if this little inequality is satisfied. Last time, I talked about, another way of talking about this, inequality. You can sort of like think about it that, if you take the product of, which one, I forget which one is which, the analysis and the synthesis operator, it has to be full rank, whatever. We won't be using, again, this like definition too much, but there it is. A and B are called the frame bounds. And, last time we discussed tight frames, and, here A equals B, that means the frame is a tight frame. But, what it kind of susses out to is like, you can define a so-called frame operator. So you have your vectors, take the outer product, and then you sum over it. So these are like little projectors onto that state. And for a tight frame, this is going to be proportional to the identity. And one implication of that is that a tight frame corresponds to a rank 1 POVM, or positive operator value measure, this generalized notion of quantum measurement that we've been discussing. If you recall, the POVM elements are like a set of, Hermitian, positive, semi-definite matrices or operators that sum to the identity. And so you can see that if we just stick in a factor, if we have a tight frame, you stick in a factor of 1 over A here, then this will like literally sum to the identity. Each of these is a, Hermitian, positive, semi-definite operator, etc. And so the idea of a tight vector frame and that of a rank 1 POVM are just the same notion. And, rank 1 meaning that these elements can be written as outer products. You can have POVMs, that have higher rank, but won't really be talking about them too much here. So for a set of normalized vectors, we could define like the frame potential. And, just from looking at this, you can see it's quite like this, where like t equals 1. So really, we could say this is the t equals 1 frame potential. And ultimately, like, this is just the trace of the frame operator squared. So then we have like a little proof here. Given some dimension d and n frame vectors, the trace of the frame operator squared, get the frame operator in view here, has to be greater than or equal to whatever is bigger, n or n squared over d. Remember, n is the number of vectors in the frame, and d is the dimension of the vectors. So there's like two cases, like this bound is achieved like if and only if either A, we have like n is less than d, in which case the vectors are all going to be orthonormal. Or the other case is we have like more vectors than the dimensionality, in which case the vectors form a tight frame if they like saturate this bound. So, there's a lot of little proofs in this paper. I kind of like adapted some, but not all of them. And, if you're seeking even more clarity, definitely check out the papers. So, here's a sort of a little proof of this. The number of non-zero eigenvalues of S has to be at most the minimum of either n or d. we have trace of S has to be equal to N, and that's also just the sum over the non-zero eigenvalues. Trace is just the sum of the eigenvalues. What is it? The N comes from the fact that, you're summing N vectors and they each have unit norm, or the outer products have unit trace. I think that's why. And then you have the trace of S squared is just, the sum over the eigenvalues squared of S. Now you can use like Cauchy-Schwarz inequality business to say that, okay, the sum over these eigenvalues squared has to be greater than or equal to the sum over Q, where that's like the number of non-zero eigenvalues that we're considering, because it's you got to divide over the number of things you're summing over, the sum over the eigenvalue squared. So, this, where is it? This is just trace of S squared. This we know has to be N squared. So you get N squared over Q, which is just minimum of N or D. And then kind of flipping the numerator and the denominator, we get that trace of S squared has to be greater than whatever's bigger, N or N squared over D. And that's what we wanted. It's funny how much of this business involves like a lot of like linear algebra stuff. I mean, just playing around with frames and designs and problems and stuff. It's like you're gonna be slinging the Cauchy-Schwarz inequality like all over the place, doing this eigenvector, this eigenvalue, that. So it's like, okay, suppose the case of N, then the eigenvalues have to be like basically 1. Because if this is N, then it's, you get N over Q is N, so it's just 1. And so therefore S is a projector onto the N-dimensional subspace, because, you have, by assumption, N less than D. Okay, so the rest of them are 0. And then we just said that each of the eigenvalues is 1, and so it's like a projector. And that implies that the vectors are orthogonal. And if N is greater than D, then we got to have the eigenvalues are N over D, which implies that S is proportional to the identity with the constant N over D. And so the vectors form a tight frame. So tight frames minimize this quantity, and it means that the vectors form a one design. So, okay. I won't maybe verbally go over like all these little algebraic manipulations in what follows, but just to give an idea, like these are like the style of proofs that go on. So this is like, we're going to talk about seq problems or symmetric informationally complete problems throughout this little lecture here. This is where we're going to introduce it, and you'll see we'll prove a little thing, and then we'll prove some other stuff in another way a little later on. So a symmetric informationally complete problem corresponds to a set of D squared normalized vectors, in complex vector space, such that the inner products are basically constant. They're all the same for vectors that aren't equal to each other, or like for vectors with different indices. So seq problems form equiangular frames. In other words, but you have some frame vectors, and for all I doesn't equal j, they make equal inner products with each other. So that's like a frame, but remember we can like, upgrade it to a problem. We'll take the outer products of each of the little frame vectors, weight them by 1 over D, and we could like write the sort of trace of the problem elements here, you know, these are just the projectors onto these states. And then, you know, there's two of them. So we took out 1 over D, got like 1 over D squared. And if you use this fact, you know, that we showed, that we were talking about, trace of S squared equals this. And, you know, you substitute in this, and, you know, you work out the algebra, you get that the trace of S squared has to be N squared over D, which is this. And so we just showed that a Sikh Pavam has to be a tight frame. Dun, dun, dun. Okay. It's tight frame, it's Pavam. Okay. Moreover, a Sikh is informationally complete. And what that means is that, like, you know, if you get the probabilities for the outcomes of such a measurement given a quantum state, then those probabilities completely nail down that quantum state. In other words, the projectors here are all linearly independent and span the space of operators. And one way of seeing this is that if you look at the Gram matrix, which is like the matrix of like the inner products, because, you know, each of these inner products is just like this, well, it's either, you know, 1 or this, then each row is just a cyclic shift of the previous row. It's just the row and then just kind of like moved over space, moved over space. And I didn't even know, this is a nice fact I didn't know. That's called a circulant matrix. And it turns out such matrices have a cool property, which is that their eigenvalues are given by the Fourier transform of like one of the rows. And in fact, in this case, the eigenvalues are exactly the same as the values in a row. And we know that, you know, it's either, you know, 1 over D plus 1 or whatever. Therefore, no eigenvalues are 0. Therefore, the Gram matrix is full rank, and, you know, ... The projectors are linearly independent, and so we have a informationally complete Pavam. So we started off talking about spherical T designs, a set of n normalized vectors such that the average value of any Tth order polynomial over the set is equal to the average of the polynomial over all normalized vectors. So, you know, this was like originally, I suppose, used in the context of, you know, real vector space, you know, originally just like the sphere, like the real Euclidean 2 sphere. But, you know, we're going to extend this idea to work with like normalized vectors in, you know, complex Hilbert space. So we got our Hilbert space, you know, complex vector space of dimension D. Now, one of the things about this paper, if you'll read it, you know, they sort of, well, never mind. I won't mention that now. Okay, so we got our Hilbert space. We'll denote like H of T to be the T-fold tensor product of such Hilbert spaces. We'll use S little t to denote the symmetric subspace. And we'll write this when we mean like we'll take a vector and then like tensor it with itself T times. So we can define a Tth order polynomial function like in the setting in terms of like a symmetric operator called big F. And so we could write, you know, F evaluated at some psi as like ultimately, you know, form a Browneket, which is like psi tensored with itself T times, okay? And then stick this symmetric operator in the middle. Now, we can decompose this guy in a nice way. So we can decompose it as like a sum over operators, which are just the tensor product of little guys acting on each of the tensor pieces. So here, you know, we have T like tensor pieces to work with. So we have like an A for each one. That's like one operator. And then we have, say, K of them. And we add those up. So,
What is A again?
sorry?
What is A?
A is just some little operator that just acts on like one of the little tensor pieces. It's, you know, kind of like a placeholder. Because this is just a sum of these little products, tensor products, we could just sort of consider, you know, just one term in that sum, like a monomial. So we could write that monomial as just like, okay, psi tensor with itself t times as a bra, psi tensor with itself t times as a ket, and then stick this operator here, which is just a tensor product of t different a's, for a's or just whatever. And we could further write this as a product where for each a, we take its expectation value with just the state psi. Which works just because, you know, these are just tensor products of psi. This is just tensor products of psi. Each one of these, the A only acts on its little piece. And so we can just kind of reformulate it this way. Then we can rewrite this itself like this. We can, instead of writing it as like this kind of bracket, we can instead write it as like the trace of A times the projector onto psi. And if we write this like big pi as just like the projector, then we could rewrite it again as just the trace of all the A's tensored together times the projectors tensored together t times. Just kind of setting the stage. Okay, here's kind of a more fun bit. So the defining property of a T design is that the average of, you know, our guy F over the design vectors is equal to the average over all normalized vectors. So we can write the average as, all right, well, here's F, and we want to integrate, you know, over all the psi's. There's that. And then actually we could move the integral like into the trace. So we could write it trace of, you know, the product of all these A's times the integral over all the possible psi's, where this is like the projector of that psi, of each psi, tensored together t times. And now by like the law of like whatever, the design thing, you know, we should be able to kind of substitute this like integral for just like an average over the design vectors in some way. So we could say, all right, well, this has got to be like some k, where k relates to the design vectors. And in fact, we'll see that a spherical design is a set of vectors for which this, which is, you could call it the Tth order frame potential, or like the T-fold tensor product analog of the frame operator. Like up here, the frame operator was defined as just this. But now we're going to imagine, instead of like, you know, psi and psi, what if it's psi tensor psi and psi tensor psi, being the ket and the bra. So we sum over those, and that's going to be equal to n times k. Now here's like a little nice thing. Yeah, I was thinking about this. I feel like I even have to, this is one element of the exposition which I feel like I should know better than I do. So, this is going to invoke Schur's lemma. And the idea here is that K has support only on the symmetric subspace because each of these is just a product of, separate tensor factors. Now, if you think about it, this K has to be invariant under like unitaries that are just like the tensor product of all the unitaries of the same unitary T times. Okay. And, that in itself is like if we take such a unitary that's like the tensor product of like the same unitary, and then we also consider like, well, what if we like permuted the different tensor pieces? Obviously, it would make a difference. And so you can like invoke Schur's lemma to show that therefore this little k has to be proportional to a projector onto the symmetric subspace. And then we can, kind of nail down like exactly what this has to be. If we just consider the constant function, then, this crap here just boils down to trace of k, okay? And it's got to be 1. The symmetric subspace has to have dimension this, little binomial coefficient there. And so we get that k has to basically be, this times a projector onto the symmetric subspace. So putting it all together, a set of normalized vectors, psi, I, whatever, with n greater than this, there's like a little bound in this case on the number of design elements. It'll form like a spherical T design, in the complex case, right? If and only if it minimizes the Tth order frame potential. In fact, this has to be this. So that's like the value it should be. And, if we specialize to the case where like T is equal to 2, that ends up being 2d to the third over d plus 1. And, if we look at the case of a seq where like we know like what the inner product squared are supposed to be, we work it out and indeed we get exactly the right number. And so a seq pavim, aka a symmetric informationally complete pavim, aka an equiangular tight frame, is also equal to a spherical 2 design. And there's another little argument that you can give that every such 2 design with d squared elements has to be a seq. Okay. So what we're trying to do is like, make a bunch of different mathematical ideas talk to each other. We have the idea of like frames, tight frames, equiangular frames, frame potential. We have the idea of a design useful for integration, integrate Tth order polynomials for a T design. And then we have the idea of a POVM, positive operator value measure, a generalized quantum measurement that can be thought of A as like a set of Hermitian positive semi-definite operators that sum to the identity, or concretely, like you have a quantum system, another quantum system, you entangle them, and then measure the like, okay, sorry, I should have said a quantum system and then like an auxiliary system, you entangle them, and then you measure the auxiliary system. And the auxiliary system ought to have as many possible dimensions as the number of POVM elements. And the probabilities will be the, basically the, the trace of the POVM elements on the density matrix. So, so there's, yeah, like these 3 worlds: POVMs, designs, frames. And we're showing that there's these very interesting correspondences between them. so that, for example, a 1 design is the same thing as a tight frame. A tight frame is the same thing as a rank 1 POVM, okay? And here we've just shown that a seek POVM or an equiangular frame is the same thing as a 2 design, a spherical 2 design. But where we're working, in complex vector space. And so, some people like to use, a slightly different set of terms. And they don't want to call it a spherical T design, but instead of complex projective T design. Because really, at this point, we're working in, with complex vectors, but, they have to be unit norm. And also, we don't care about the phase. So, when we form like a projector, we're throwing out the phase. So you can think about complex projective space as a space of lines passing through the origin in, CD. And, basically you can think of them as like rank 1 projectors. And so you lose a bit of the dimensionality because, you're throwing out the phase and also you're demanding that this have, trace 1 or like the vectors be normalized. So, all right, let's not get bogged down in this. This is just sort of rehashing basically the argument we gave above, but just more like in complex projective design terms. So, you see here, if we integrate over all of complex projective space, D-1, these projectors, which are like a given projector on a given psi tensored with itself T times, this has got to be a projector onto the symmetric, the totally symmetric subspace. Yeah, so, tight T designs for complex projective space dimension 1 are just the same as tight spherical T designs on the Euclidean 2 sphere, okay? Tight 1 designs exist in all dimensions. Tight 2 designs, whether they exist for all dimensions is just the famous question of like whether seeks exist for all complex dimensions. And it's conjectured to be true and no one knows. We can also sort of like extend the notion to like a weighted T design where like now, each of the projectors has like a little weight. If you look at this up here, we sort of implicitly had a weight of 1/n on each of these guys. But you can have different things. And it's worth noting that, a weighted T design, or just an unweighted T design too, is also a T-1 design. Which you can see from the fact that like if we were to trace over like one of these tensor pieces, we'd still get a projector onto like the symmetric subspace. So anyway, let's basically do the same kind of numerical optimization to like find a seek, find a complex projective 2 design, etc. So, one thing, if you're doing this kind of numerical optimization is like sometimes you got to kind of play around to make it work nice with complex numbers. So, we actually work with real vectors and kind of, take them and turn them into complex vectors and back, just because the optimizer doesn't like working with complex numbers directly. But, basically, this is like the same thing we had before. I'm going to minimize the frame potential, make sure we got unit norm. And we'll do it. And again, you could try to go for higher tolerance, in other words, like more accuracy. But, it can sort of be annoying. Just to save time here. So we showed up here, if you recall, that the frame potential, second order frame potential for a seek has to be 2 times d to the 3rd over d plus 1. And that's like the minimum value. And so we can see that we got pretty darn close. 5.33333, whatever. And now let's check. We should have that if we take the projectors for each of these seek states and we tensor two of them together, or like tensor the same one with itself, okay? And then like add them up, we should get something proportional to a projector onto the symmetric subspace with these little, with these little coefficients. So this is some code which, creates a projector onto like a symmetric subspace. So for example, the classic case, which, we should all be familiar with, is like, we're going to work mainly, throughout in like 2 dimensions. So here we look at the eigenvalues and eigenvectors of the symmetric projector, and like, what do we find? Here's like the columns here are the possible states. Okay. And you notice the eigenvalues are either 1 or 0. And the only 0 is for this state, which is like the anti-symmetric state. So these 3 remaining are, permutation symmetric. So indeed, this is a projector onto the symmetric subspace. If we, this will give us this part of the formula, 2 over d times d plus 1 times the symmetric projector. It looks like this. And then if we take this seek that we found and we form, this tensor product of the projectors tensored with themselves times 1 over d squared, we get exactly that same thing. And so, you could go further, right? Like, if we're interested for whatever reason in like t equals 3, then you'd have a projector on the symmetric subspace of like 3 copies of the 2-dimensional Hilbert space. And then this would be a sum over, pi I tensor pi I. So, there's, and incidentally, if you look in the literature, people have, thought long and hard about the question of like finding seeks numerically. And, this, which we did here, is pretty much like the simplest thing you can do. Like you see, like it kind of worked ish, it wasn't exactly that accurate. But, there's various tricks you can do, both like in terms of like at the level like this kind of optimization, but also ways of like simplifying the problem, using knowledge of the structure of seeks and so forth. And so there's like, several interesting papers if you look it up. There's a nice paper called like the seek question. State of play, the state of play, history and state of play. They go into a little bit about how various tricks people found to like find seeks, for dimensions much greater than 2. Okay. So now we're going to sort of think about another concept, which is out of an operator frame. So it's like, before we were discussing vector frames. And now we're going to just generalize that notion to operators. And we'll have recourse to thinking about like the vectorized version of an operator, which we'll write like this, where we kind of have this like a little parenthesis instead of an angle bracket. And this is like, if you have like a operator A, you just, reshape this matrix into a vector. So it's like this one, this, and then this part goes like over here. Blah, blah, blah. It's like unwind the matrix like into a vector. And the Hilbert-Schmidt inner product on the matrices, which is like the trace of A dagger B, is just, this, like the normal bracket between the vectorized versions of the operators. And, why do we want to do this? Well, there's lots of interesting reasons, but one is that it allows us to play around with super operators in an elegant way. So what's a super operator? Nothing to do with supersymmetry or anything. Super operators are just linear maps on not states, but operators. So suppose we fix some orthonormal operator basis such that like any two elements are just given, the inner product of any two elements is just given by delta ij. For complex dimension D, this will have D squared elements. And we can define a super operator in two ways. So this first way gives us the ordinary action. So in other words, what this means is these are just like operator basis elements, any orthonormal basis you like, got some coefficients, Sij. And the idea is you take the sum, but like in this little dot here, you stick your operator. In other words, if you wanted to evaluate, the map on some matrix A, you would stick A in there and take the sum. But you could also sort of think about the so-called left-right action of the super operator. So that would be, you would like, writing it in this way, you would sort of go over all of these little operator basis elements. You would vectorize them, right? And this will give you some matrix. And it acts on like the vectorized version of the operator A. So in other words, you can have an operator A, and then you can sort of evolve it with your super operator by kind of wedging it in the middle of like these guys. Or you can like vectorize these and get a matrix, and then this one will act on the vectorized version of the operator. So for example, like this will come up, we'll think about like the identity super operator. So we can think about this as like either, identity on the left, identity on the right, where we stick some matrix in the middle, kind of trivial. Or as like take the identity operator, unwind it into a vector, take the outer product with itself, and we get this. So this is like the left-right version of it. We can also think about the super operator identity itself, which is just like a sum over the outer products of the basis elements, which just ends up being like the identity in the dimension of the super operator. So like we've been working with, complex dimension 2. And so, the super operators in the left-right formulation will be like these 4x4 matrices. So n here, is D squared. That's just constructing a little operator basis, and we're checking that it is indeed orthonormal, whatever. Anyway, so we can just sort of generalize our notion of a vector frame to that of an operator frame. So this is just like that same inequality that we saw like way up here. Okay, this guy. But we're going to be thinking about like basically vectorized operators instead of just vectors. So we get that. And just as before, if A equals B, we have a tight frame. And then interestingly, for an operator frame with D squared elements, the frame being tight, the operator frame being tight, means that it is in fact an orthonormal basis. For any operator frame, we can find the dual frame such that if we vectorize the dual elements, vectorize the operator frame elements, take this little outer product and the sum, we get the identity. or remember, this is the 4x4 identity. And then we have, you know, like when we were talking about frames, the reconstruction formulas. So in other words, I can write any C as either the dual elements weighted by the inner product with the normal elements, or the normal elements weighted by the inner product with the dual elements. In other words, if you take your inner products with the, you know, operator frame elements, in order to reconstruct the operator that you represented, those have to become the weights on the dual. Or you can take inner products with the dual elements, and those become the weights on the elements themselves. So, you know, sometimes there's wiggle room about like what is the dual frame. It's not uniquely defined, particularly when you have more elements in your operator frame than are necessary to span the operator space. But there's a canonical choice, which is defined in terms of the frame super operator. So, you know, we talked about the frame operator, you know, which was just this. Now we're going to talk about the frame super operator, where these, recall, are the vectorized versions of the operators that make up the frame. And we just sort of sum over them in the same way. If we take the inverse of this matrix and have it act on the vectorized versions of the operator frame, we'll get the dual elements. And then you can see that this business here is in fact automatically satisfied, because, you know, each DI is just F inverse on EI. So we have that, we can rewrite it like this, but this is just the frame super operator. And so we get F inverse times F, which is the identity. So just as for a normal vector frame, for a tight operator frame, this F is going to be proportional to the identity. And so the duals are proportional to the elements. And if you recall from something I mentioned, you know, previously, or like last time, this means that a tight operator frame can't be a POVM, because POVM elements are positive semi-definite. And in general, their dual elements have to be indefinite. Okay, and so therefore, they can't be proportional to each other. All right. So we sort of generalized the notion of a frame, of a vector frame, to that of an operator frame. But we've sort of lost a bit of our connection to POVMs and quantum measurements, because a tight operator frame is not a POVM. In other words, a tight vector frame was a POVM. In fact, it was a rank 1 POVM. That was the whole idea. We have each POVM element is like proportional to a projector onto the frame vectors, and the condition of tightness was that this has to sum to the identity, which was just the constraint on a POVM, that the elements have to sum to the identity. So like a rank 1 POVM is the same thing as a tight vector frame. But, all right, and a tight operator frame, in contrast, can't be a POVM. You know, I have to say, 90% of the effort in putting this together is like getting all this terminology straight, okay? So if your head's spinning, it's okay. Mine is, well, was and still is spinning as well. So, okay, but like, let's play around with operator frames anyway, even if they're not POVMs. So, you know, when we talked about vector frames, it turned out that pretty much like any old random set of vectors with probability 1 would give you a vector frame. Because if you just choose a bunch of random vectors, you know, it's almost certain that they will be linearly independent. And the same is true for these matrices. So we can actually just like get an operator frame by just choosing, like in this case, we want d squared because the operator space is d squared. We want to span space of operators. D squared, just like completely random matrices full of complex numbers. We form the frame operator, which recall is we like vectorize each of the elements and take the outer products with themselves and add them up. We get F inverse, which is the inverse of that matrix. And then we get the dual frame by acting with F inverse on the vectorized elements, which gives us a vectorized version of the dual, and then we reshape it back into a matrix. So we get that. And when we do this, we can see that the inner product between an element and a dual is just 1. And we can see if we just choose a random, say, density matrix, here it is, rho, we can expand it in operator frame elements. So we go over each of the elements in the operator frame, take the trace with rho, and we get these 4 numbers, which are like just generally complex numbers. Alternatively, we could expand rho in the dual elements, take the trace with each of the duals. So we get these coefficients. And if we take this first set of coefficients and we take a sum weighting the dual elements, we recover the original rho. There it is, 7, 4, 3, 2, 3, 2, 2, 5, 7, 4, 3, 2, 3, 2, 2, 5. So, as the classic thing, inner product with the elements become the weights on the duals. And similarly, the inner products with the duals become the weights on the elements. And so we can recover our rho. And finally, we can check that, the sum of an outer product with the dual and the element summed over all of them is just the identity. But, that's just like some random old operator frame. That's how you can use it. We just did it. We just expanded an operator in terms of an operator frame and then reconstructed it using the canonical dual frame. But we were also interested in these like tight operator frames where the frame operator was just proportional to the identity, so that the frame elements and their duals were also proportional to each other. And in fact, I said that they had to correspond to an orthonormal basis, actually. So there's actually a trick for just randomly generating these, which is just to take the, basically the matrix square root of the inverse, well, f to the -1/2 of the frame operator. So if we, do that and act with that on each of the frame operator frame elements, we'll get a new set of operator frame elements, and they'll be tight. And what that means is that if we, make the frame operator, as you see here, is just the identity. So that if we have some rho and we expand it in these like tight operator frame elements, then those very same numbers end up weighting, the operator frame elements in your reconstruction of rho. In other words, the elements and their duals are just the same. So we can recover rho by just weighting the elements themselves by the trace of rho on that element. And here's just, a little inequality that, whatever. Okay, so we began by talking about designs. Like, designs are cool. They help you integrate stuff. It's like a set of vectors that have this property. They minimize the frame potential. It turned out that one designs were the same thing as frames, tight frames. Yeah, tight frames. Turned out rank 1 tight frames were the same thing as rank 1 problems. Sorry, I should have just tight vector frames are the same as rank 1 POVMs. Talked about seeks, trying to bring together designs, frames, and quantum measurements. We then tried to think about like an operator frame. And that was cool, but like we lost our connection to the quantum measurements because we want POVMs, which are like things we can do in the lab, but operator frames aren't POVMs. So what can we do? We want a notion, indeed, a notion which will help us understand the nature of like seeks, for example, like why they're so cool. So we want like a notion, some kind of notion, basically of like a tight, informationally complete POVM, some kind of generalization of the notion of a tight operator frame that's appropriate for POVMs, because like we know that we can't technically satisfy the definition of a tight operator frame with a POVM. So that's where we're going to go. And then we're going to show that like they're optimal for tomography or state reconstruction. So just to establish a couple conventions briefly, here's a nice way of generating a random POVM where, you know, you can have like any number of elements. You can sort of adjust the mixedness of each of the elements, and also the elements will be of different weights. You have to sum the identity, but you might have to, you know, sort of multiply them by different numbers. And, you know, it's, as you see here, use of frac. I won't go into, I talked about this algorithm, I think, in another little meetup, but ultimately, morally, it's doing the same thing that we did here when we got a tight frame, tight operator frame. You know, basically generate a bunch of random matrices that are positive semi-definite. You know, you take the sum of them, and then you take, you know, the negative half power, and then, you know, you multiply each of the matrices by that, and it then imposes that those matrices have to sum to the identity. So anyway, it generates a random POVM. We'll denote by PI the normalized elements. In the case of a rank 1 POVM, these will be projectors, but that's not necessarily true. And then we'll define the POVM superoperator in like this. So it's basically that like frame superoperator we're talking about, but we're just being a little bit more careful about like the normalization. So here we have the outer product of the vectorized versions of the normalized elements, the PIs. And then we're like gonna weight that by the trace of the original trace of EI. Why do we do that? Well, if we do that, we will get, if we look then at the eigenvalues and eigenvectors of F, we'll see that it'll have the vectorized version of the identity matrix as an eigenvector with eigenvalue 1. So that's how we're going to like normalize things. So here, there's F acting on the vectorized version of the identity, and it just leaves it exactly the same. So in general, these POVMs might have different weights. In other words, the weights are this like little trace here. In the case where, you know, they all have like the same weight or the same trace, we could just write F where they all have just weight D over N. And then we'll get that. And, you know, as I've said, we're interested in POVMs which are informationally complete, and that will mean that the frame superoperator has to have full rank. Okay, so now we're kind of like coming into the sort of the final, the getting close to the punchline here. Tight, informationally complete POVMs. How are we going to define them? So first, we're going to think about how we can embed the space of quantum states or density operators into R d squared minus 1. So this, in the case of dimension 2, turns out to just be the Bloch sphere representation. So what we do is we take all of our states, rho, and we subtract off 1 over d times the identity. And since the rows, all have like trace 1, this will lead to like rho becoming a traceless Hermitian operator. And if we, define a little inner product in the norm, it'll turn out that the set of all traceless Hermitian operators forms a real inner product space. And so, what this will mean is that pure states will live on the surface of a sphere, a d squared minus 2 sphere. And if we look at so this is, projector here corresponding to a pure state. We subtract that off. So now this is traceless. And then we, take the norm, it's going to be square root of d minus 1 over d. And so that's going to be the radius of the sphere. I mean, with a different normalization, like you could make that 1 or something. So pure states will live on the surface of the sphere. Mixed states will live inside the sphere. And as I say, for d equals 2, this is just the classic Bloch sphere representation. Pure states live on the sphere. Mixed states live inside the sphere. The maximally mixed state is in the center of the sphere. But, you can basically do that same trick for higher dimensions. And it's just more difficult to visualize and, has some slightly different properties. I mean, d equals 2 is kind of special. But. So basically what we want to do is we're taking all of our states and we're going to kind of map them into the space of traceless Hermitian operators. And what we're going to be interested in is, can we have a Pavam that's a tight operator frame for the space of traceless Hermitian matrices? Before, we were just considering an operator frame for just the space of operators, whatever. But what we're going to try to do is think about operators frames specifically for this subspace of traceless matrices. So suppose we have some, Pavam superoperator. We're denoting its normalized elements P of I. We could rewrite, so normally, this would just be, F would just be sum over trace of EI, that's the weight. And then we'd have the outer product of PI with itself. But we could rewrite it. Instead, we're going to work with PI traceless version, where we're subtracting off the identity over D. Outer product with the vectorized version of the traceless version. Still got this weight here. And then we're going to put back that stuff that we subtracted off over here, where this is the identity superoperator, where I is just the vectorized version of the identity, outer producted with itself. So that's just some fiddling around. We're rewrite it that way. And so we can see we'll generate a random Pavam, these are the normalized elements. We can see here we're taking this is just basically this. This is just the usual formula for the superoperator. So we go over each of the normalized elements, vectorize them, outer product, multiply by the trace, take the sum. There it is, F. Here's that identity superoperator. And then this is just this formula from here. So, we're subtracting off the little trace full piece and then adding it back over here. And you can see that this is just the same as that. So that's just this formula. Just checking it out. So if we think about this little identity superoperator here, which, as I say, is just the outer product of the vectorized version of the identity with itself, you look at its eigenvalues and eigenvectors, Well, what does it do? It left-right projects onto the subspace spanned by the identity. In other words, eigenvalues all 0 except 1, 1, and that corresponds to this column here. And if you took that column and like reshaped it into a matrix, like that's just the identity matrix, like, you know, up to normalization, 1, 0, 0, 1, 1, 0, 0, 1. Therefore, if we took the orthogonal complement of this, in other words, you took this guy and you did like the identity, 4x4 identity minus that, you would get a projector on to the subspace of traceless operators, because these other guys are all traceless. In other words, this is just 0, 1, 0, 0, right? It's got zeros along the diagonal. This is like 0, 0, 1, 0. That's zeros along the diagonal. And this is like -1, 0, 0, 1. So -1 and 1, they add up to 0. So, you know, these three guys here are like traceless. And so we can define pi0 as this, and it'll be a projector onto this subspace that we're interested in, the space of traceless Hermitian operators. So there it is. There's our pi0. And we can see, you know, it's just here, the identity, which has, you know, trace, like a non-zero trace, is the only one that has eigenvalue corresponding to 0. So, you know, before we were kind of writing it, you take like rho and you subtract off the identity over D. Well, this operator pi0 like does this, realizes this embedding into what some people call the block body. Funny pun. So you can see here we have some rho. We can do our projection, and we can just literally subtract it off, and we see we get the same thing. So we'll denote I0 to be the left-right identity superoperator for the space of traceless Hermitian operators. And here's the punchline. Okay, we're going to define a tight, informationally complete problem to be one for whose elements, where remember P is like the normalized version of problem element, minus you know, 1 over the identity. In other words, we take each problem element. Oh, I should put like a little p either. Take each element, normalize it, subtract off identity over D. Now I've got this traceless guy. If we then form like the frame operator for those guys, which is just this, where here we've got our weight, then that has to be proportional to the identity on this space of traceless operators. So another way of saying this is that if we stick F, the frame operator, in the middle of 2 pi zeros, we just have to get something proportional to pi0. In other words, if we just had, so if we recall the definition of F here, it's like if we act with pi0 on the left, this P is going to turn into P minus I over D. When we act with pi0 on the right, this is going to turn into Pi minus identity over D. And so this is going to end up being just this. And, you know, what is this identity, you know, on the space of traceless operators? It's just going to be that projector, like which projects onto that subspace. So, you know, earlier in our numerical adventures, we found a seek. So, you know, let's see if, well, you know, anticipating somewhat. So we're going to prove that seeks are in fact tight, informationally complete problems. But we'll see, in fact, right now that like the seeks satisfy this. So we generated our seek. Here are the elements. Here's the normalized elements P, and then we form F, and then we, you know, do Pi0 times F times Pi0, and here's pi0. And you see that they are, it's easier to see if we just do like real, that they are indeed proportional to each other. Well, you know, if you eyeball it, like, are they really proportional to each other? They are. And we're about to calculate what the constant of proportionality is. So how do we do that? We're just basically going to take just this, which is basically the trace of this, of like the frame operator, that, you know, where the elements are the traceless versions. It's basically the trace of this, right? That makes sense, right? Like the trace of this is, you know, A over whatever, N. Yeah. So, you know, if these are actually equal, we're just sort of interested in the trace of this. So, yeah. Oh, yeah. And we get d squared minus 1 because we're in the, you know, we threw out a dimension when we did this little map here. So that's where that's coming from. In any case, we plug in the stuff that we found when we generated our seek, and we get that A has to be a third, or like close to a third. And indeed, if we multiply pi0 by a third, we get that, which is exactly this that we found. So pi0 times f times pi0 is 1/3 times pi0 for this seek in 2 dimensions. And so, you know, we can kind of fill around a bit. We can actually like do, you know, a lot of like simplification. So we could write f as this, where, you know, this weird looking I, you know, is the identity superoperator. We take like up, you know, the identity, vectorize it, take the outer product with itself. This is just the identity, you know, in the, you know, this is identity in like, you know, whatever, d squared dimensions or n dimensions. So we can write this, write f like this in these sort of more sort of simple ways. So you can see that this works, get the same matrix. And similarly, there's like a cool little formula for f inverse. And, you know, you see, it's like, yeah, it's like, it's mostly right. I mean, there's a little error just because, you know, we're numerically approximating the seek. And similarly, we can get a nice, cute little formula for the dual elements. And as well, a cute little formula for, you know, state reconstruction, where, you know, these are these guys are, you know, the probabilities for the Pavim outcomes given rho. You know, see, it's the inner product with Pavim outcomes with rho, etc. Simplifying even further, in the case of a tight rank 1 informationally complete Pavim, we just have A equals 1 over D plus 1, and that is what we had. And then we can really simplify F to just that, which, as you can see, is true. And the state reconstruction formula simplifies even more to just that. So this is pretty cool. So like, remember, when we were talking about, you know, you have your elements, your Pavim elements, say, okay. Thinking about operator frames, right? You have your operator frame elements, and then you have your dual elements. You take your inner products with, you know, the matrix you're interested in with the elements, and those turn out to weight the duals. Take your inner products with the duals, and they turn out to weight the elements in the reconstruction of the state. Tight operator frames were cool because the elements and the duals were proportional to each other. So like, you didn't even have to worry about the duals. Basically, you could just take the inner product with the elements, and then those turned out to weight the elements, sum over it, get back your operator. We then were like, oh shit, you know, tight operator frames are great, but they don't correspond to POVMs. They're not going to be useful actually doing things in the lab, doing quantum state tomography or whatever. You have your POVM elements, you have your POVM dual elements, but they can't be the same. They like literally can't be the same. POVM elements have to be Hermitian and positive semi-definite. The dual elements in general will be indefinite matrices. So a tight operator frame can't be a POVM. Then the question is like, well, what's the best you can do? And thus we were led to the notion of a tight, informationally complete POVM, which is defined here, where we basically are interested in taking the states, projecting them into the space of traceless operators, and then demanding that we have a tight operator frame for that subspace. And so if we do that, you can see that we can write the state reconstruction formula in a way that's like really, really simple, like arguably as simple as you can get, given the fact that a POVM can't be a tight operator frame. In other words, we can get our probabilities, which are inner products with the POVM elements. Normally, we would like have to take the, find the dual elements, and then those would weight those. But, we can actually like write this much simpler formula. Or we can, if we have our probabilities on the elements, we just use them indeed to just weight the projector of the element, right? Like no dual in sight, but we got to multiply by d+1 over here. We got to subtract off the identity. Is this useful? Yeah, I mean, this sort of connects up with some stuff we were talking about before, I guess. So we can rewrite F, the frame super operator like this. And we can write it in terms of the ordinary action now. Where remember, we like stick some matrix we're going to act on in this little dot. And it'll turn out that like, okay, so these are the POVM, like normalized elements of projectors, and here's like the weight. Because we had this, which is just this, we can rewrite it as just this, where this is just some orthonormal operator basis, and it's just like the identity. So, this just shows that in fact works. This is just the left-hand side. This is just the right-hand side. We can also rewrite that in terms of the left-right action, which amounts to replacing these little dudes, the little sockets, with tensor products. And indeed, when we do that, well, this just looks horrendous because it's like around that a little bit, little numerical error there. Decimals equals 30. Yeah, we basically get what we wanted. That's the frame super operator as we found. So, we can, rewrite things in such a way, not to belabor the details, where we can kind of like write this as like the swap operator, bit, 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 bit. Point is, we can rewrite this as, you'll never guess, a projector onto the symmetric subspace. And so this connects back up with what we where we started way back when. Where we here we sort of like invoked Schur's lemma or whatever, and figured out that this has to be a projector onto the symmetric subspace, et cetera, et cetera. And so now we basically rederive that from a different direction. So, yeah, all right. So a tight informationally complete POVM is a 2 design. And indeed, the unique minimal rank 1 informationally complete POVM in each dimension that has d squared elements corresponds to a seq. You might wonder though, so the seqs are like minimal, they're like tight IC POVMs, that's great. Are there like other examples that we can talk about? And actually, there is a very simple example that, makes a lot of sort of intuitive sense. Another example of a tight rank 1 informationally complete POVM is a set of so-called mutually unbiased bases, or MUBs. Okay, so they're a set of d+1 orthonormal bases with constant overlap 1/d between elements of different bases. You're like, okay, what the heck does that mean? Well, just take your Pauli matrices and you look at the eigenvectors of them. And then, form the projector onto each of these vectors and make a list of them. They will form one of these MUBs, right? d+1 orthonormal bases, right? So d in this case is 2. So we need 3 orthonormal bases. And indeed, the eigenvectors of Pauli XYZ form each orthonormal bases for C2. And here, this just checks, look at all the inner products between the elements, and it does have that property. And we can show, just like the seq POVM that we were studying, if we oh, well, which is the right one? Oh, yeah, I guess there's like a bug here. Well, in the case of a seq, we're looking at, this business being proportional to projector onto the symmetric subspace. And indeed, if we take the tensor products of each element in the MUB with itself, it too is proportional to a projector into the symmetric subspace. And oh yeah, that's what this is. This is supposed to be what is that, right? What did F, sorry, I'm just, I'm just making, just confusing myself here. F, so there's that. And there's that. Oh yeah, that's right, sorry, yeah. And so this is the frame superoperator for the mutually unbiased bases. And you see it's like the same as in the case of the seq. I just got confused. These look so similar. I was like, which one's supposed to be which again? Anyway. So, all right, so let's wrap up. The final little thing is just a gesture towards a proof that what makes these guys great, tight informationally complete POVMs, is that they're optimal for so-called linear state tomography, or like state reconstruction. So I won't dwell too much on this, but basically, so we're going to say do some POVM, n times, and get a bunch of samples, and we could like write our estimate of like the probability in this way, which is just sort of annoying looking, with like a little delta function, a little delta, or Kronecker delta, whatever. It's just saying, okay, for I, go over all the samples, set all the samples for a different outcome to 0, add up all the ones where, that outcome happened, assign it value 1, divide over the number of samples, and you just get, the reconstructed probability. So after some algebra, you might be interested in the expected covariance of after n samples, which it turns out you can write like this. And we're going to just use that little fact in a moment. So given, the samples, our estimate for this like density matrix that we're trying to reconstruct is going to be this. Why? Because this row with this P with a hat, those are just the probabilities we're reconstructing. Like we're doing our measurements, we're like accumulating counts, we're dividing by the number of experiments that we did, we're, getting these empirical sort of probabilities. And we know that those guys are supposed to weight the dual elements of the POVM in order to get this. And then we have 1 over trace of EI, and that's the weight. So we could be like, the error of the estimate is like rho, the actual rho, right? Minus the reconstructed rho, given some finite number of samples. So we're just going to use, the Frobenius norm. And, if you work it out, you can kind of like, you basically, you'll write rho and rho hat like in these terms, and then you'll end up with all this juicy stuff here, and then you'll have inner products with the different DIs. So then we can write the expectation value of the error like this. It's sort of annoying keeping track of all the traces and stuff. We're dividing by the number of samples. Here, we just use this rewriting of the expected covariance. And then because this little Kronecker delta is in there, we can sort of turn this double sum into a single sum. We get this. Details don't matter that much, but the point is, if we basically what we want to do is we want to minimize the expectation value of the error. And so we're not going to be able to control the trace of rho squared, but basically we can play around with this term. So the question is, how small can we get this? Now, the problem is that, the POVM which minimizes this quantity, like what you see, depends on a particular state, these PIs, is going to depend on the state. So what we really ought to do is like average over all the states. So we'll set rho to, basically some unitary times some sigma times unitary adjoint. And then we're going to like integrate over, all the unitaries. So here what we've done is just taken this. We rewrote, what is PI, right? It's just trace of EI on rho. And what is rho but U times sigma times U dagger? So that's just this. And then we have our little weight and and then we're subbing over, we're integrating over, unitary group. And then, I trust the paper to tell me that, because I have to confess my inexperience in integrating over groups and thingies, that it works out to be this. And so, this trace of EI is going to cancel out with one of these. Trace of sigma, sigma is just a density matrix. It's got to have trace 1. And so we end up with this. But what is this? This is just trace of the frame superoperator, the inverse of the frame superoperator. So if we want to minimize the the expected reconstruction error, then we want to minimize the trace of the inverse of the frame superoperator. So this is a little cute proof that, like here, when we invoke these Ds, we're basically talking about the canonical, quote unquote, dual. Like in other words, take the frame operator, take its inverse, act on the vectorized versions of the elements, you'll get these canonical duals. So the question is like, well, what if you use some other dual or like whatever? And what we're going to show is that you can't do better, like with regard to this, trace of the inverse of F inverse than the canonical dual frame. And so, it's just a little algebra. I won't go into the details. And at the end of the day, we can get a bound that trace of inverse of the frame superoperator has to be greater than or equal this thing. And where does that come from? Well, you'll write the trace as like the sum over 1 over the eigenvalues of f, because remember f inverse is just the inverse of f. We know that trace of f is just the sum of the eigenvalues. And, that is sort of bounded above by d. Because ultimately the trace of these little guys, which are normalized, trace of the guys squared has to be less than or equal to 1, because they themselves have trace 1. And we also know, as we've had recourse to mention before, the identity operator is a left-right eigenvector of f with eigenvalue 1. So we can kind of like take that out, counting from 2. And work in the numbers, you ultimately get that the eigenvalues have to be 1 over d plus 1. And indeed, like when we were talking about the Gram matrix of a seq, we were like, oh, it's a circulant matrix. The eigenvalues are basically, the same as the elements in a row. And what are, the famous seq, traces, but 1 over d plus 1. And indeed, this fits with what our little, fancy decomposition of f for a tight information complete POVM, where this is just the case of eigenvalue 1. And this is the case of the other eigenvalues. And so trace of, f inverse takes its minimum if and only if f corresponds to a tight rank 1 IC POVM. And, this is where this comes from, because, one of the eigenvalues is 1. The rest of the eigenvalues, there's d squared in total, are d plus 1. Right, because remember that this is the eigenvalue of f, and so the eigenvalue of f inverse is 1 over that. So we get that. And indeed, we'll check it out in the case of our seq. And indeed, this for dimension 2 is 10. We take the inverse of our f super operator, and it's 10. So, that's the sketch of a proof, basically, that, it's optimal to use these kinds of constructions to do quantum state reconstruction. You might be interested in like nonlinear quantum state reconstruction. You might be interested in like, well, what if I have like partial knowledge of the state already? What measurements should I do? These are all more complicated questions. But anyway, that's pretty much it. Just to recap where we went, it's like, talked about designs, set of design vectors, useful for doing numerical integration. And we talked about the relationship to frame theory. Frames are like these generalizations of bases where you can have, an over-complete set, greater than the possible number of linearly independent vectors. We showed that a 1 design and a tight frame are the same thing. A tight frame is the same as a POVM. So that was like our third sort of world that we tried to, bring into the conversation, the world of, positive operator value measures, these generalized quantum measurements. And we then, talked a bit about optimizing both, spherical designs, but also these complex projective designs. We talked about operator frames, which can't be POVMs. And so we were interested in tight operator frames because the elements were proportional to their duals. And so the reconstruction formula was simple. So then we had this idea of generalizing this concept that this paper calls tight informationally complete POVMs, where they do form a tight operator frame, but not for, but in the subspace of traceless operators. And that, mapping into the subspace is, what we do in any case when we, use the classic block sphere representation or whatever. And so then we showed that an example, in fact, the minimal example of a tight informationally complete POVM is a seq. There's other examples, mutually unbiased bases. And, because the state reconstruction formula is like as simple as possible, you might say, they're optimal for doing state reconstruction using these special kinds of measurements. And so we gave this proof, which, I may have breezed over certain steps in just for the sake of time. There's like this little proof that, if we have a tight informationally complete POVM, a tight rank 1, like a seq, informationally complete POVM, this value, trace of the inverse of the superoperator, will take a minimum, and that will imply that the expected error of the reconstruction will be as little as possible. And so that's why these guys are good. So anyway, I invite you all to check out these two references. Some of the notation's different. I tried to simplify things, but also I subtracted some things. There's more detailed proofs and so forth in here, particularly this one. So if you're interested in more, check these out. So we had a small group today. I hope that you guys enjoyed it. Whether you're awake or asleep, fine by me. We got it all recorded, it's in the can,
Thanks for the presentation, appreciate. One comment, if I may, more of a general comment, and it's really up to you. I think what would be helpful to folks like myself is if you start with a real problem, you're in a laboratory or whatever, and you want to do something, and here is why the problem is difficult, why there is no solution to the problem, or difficult to do it, or whatever. And this is how we're going to try to solve it. And as you go along, try to relate it to this problem. Okay, in the case of this problem, using this as an example, here is what we get. And here is why we have to go through the next step. At this point, okay, this is the hurdle that pops up, and this is how we are going to address it. So just a suggestion.
Yeah. I mean, you're right. The physical problem, which is at the heart of this, is doing state reconstruction, right? So it's like you have some unknown quantum state and you want to know what it is. And so what are the simplest, most efficient set of measurements that you can do to figure out what state you're dealing with? Yeah. And so this whole thing is, theorizing around what might these optimal measurements look like. And word on the street is there's these seq POVMs. And so the idea was to prove a bunch of properties of them and sort of discuss why they have to be the best or whatever. But yeah, I mean, it would have been interesting, I agree, to consider, a bunch of different things, that aren't seqs, aren't tight informationally complete POVMs, and show how worse they do. I realized that this particular talk was kind of proof heavy, I was sticking very close to this one particular paper. So I don't know. I apologize for that, I guess.
No.
But yeah, it was. I think this was particularly proof heavy today, for better or worse.
But again, along the presentation, along the proof, if you can tie it to some very specific and very concrete example.
Yeah, well, I mean, we were working with dimension 2, so just have in your head, we're just trying to figure out what's the state of a qubit. I mean, because remember, I should have reminded you that, what does this seq that we played around with even look like? If you look at the 4 states, they form a tetrahedron, a regular tetrahedron, like in the Bloch sphere. So there's these like 4 special states on the Bloch sphere. And the 4 outcomes of this generalized measurement will allow you to most optimally, most efficiently reconstruct the unknown state of a qubit. And so materially, it's like you have your qubit, it's 2-dimensional. You have some apparatus, which is 4-dimensional. It's got to be d squared. And then to implement the POVM, there's going to be some unitary that's going to entangle the qubit with the apparatus. And if you look at the probabilities of like the 4 outcomes of a measurement, a normal measurement on the apparatus, it's going to be given by like the trace of rho on the 4 POVM elements. And so you'll get those 4 probabilities that like we get here. And if you make the measurement on the apparatus and say you get like this outcome, then afterwards the qubit will be steered to the state that's like at one of the vertices of the tetrahedron. If you get this measurement, it'll be like one of the other vertices of a tetrahedron. So like the 4 outcomes to the experiment correspond to the 4 vertices of the tetrahedron. So, I mean, I don't know if that's more concrete, but like that's what it would be like.
Yeah, it helps, definitely, yes.
Yeah, Matt. So I'm not very good at this area, so thank you so much, because this was a lot of great information. But I think like quantum state tomography, I think it's going to find applications in quantum error correction. It's just that devices aren't advanced enough right now where we can implement any of this. But no, this was amazing. But that's the best real world example I can think of. I mean, it's real broad. It's much broader than that, but there'll be a lot of applications once we can have the everything to implement it with.
Yeah, I mean, and indeed, like one thing I'd love to do sometime is figure out like a quantum algorithm for finding seeks themselves. Like in other words, this little guy, this code here, very simply, did that numerical optimization, wherever it was, and found this little tetrahedron, basically. There's like, people use like a giant supercomputer, like at the University of Massachusetts, to calculate seeks, up to, I don't know, dimension something or other. I think it's less than 200 though. It's like very complicated. And indeed, like in this era when we only have a few qubits, like it's not that big of a deal, like, you know what I mean? But, if you want to use it in the context of quantum computing, but like, yeah, one kind of project I've been thinking about is like, using some of these like variational quantum algorithms and stuff to like implement like this, something analogous to this little search here, and use the quantum computers themselves to like find these optimal measurements for tomography. We'll see. I mean, if you have any ideas, worth playing around with that kind of thing. Yeah. And if you look in the literature, this type of stuff is, it'll be more specialized sometimes, to talk about, optimal POVMs for, reconstructing states of, whatever, photons or like, different stuff. What's cool about these results is, they really just depend on, you're just like working in just Hilbert space of dimension D. It's like, what's, you got to have at least D squared operators to span the operator space. And it's like, what's the optimal one? And it's going to be one of these symmetric informationally complete ones. But of course, nobody's proven that the seeks exist in all dimensions. So that's like another huge open question. Like if they exist, they're optimal. And in every dimension anyone's ever looked, they found one, or the computers kept running and they got bored. Whereas, last time, right, I I talked mainly about this stuff, but in the real case for like real vector space instead of complex vector space, right? And there it's known that these seeks don't exist in all dimensions. They don't exist in dimension 4, dimension 5, whatever. So like it's known for real vector space that seeks don't generally exist. For complex vector space, it's been conjectured that they exist, that there's like a complex projective 2 design in any dimension. So if you can prove that that they really do exist, that would be huge and would have implications in, you know, not just in quantum mechanics, but apparently in all sorts of more obscure corners of mathematics. Yeah, any other questions or concerns or thoughts? Yeah, I mean, thanks again for sticking with it. I realized even as I as I was going through this, you know, I was like, I probably should have left out some of these sort of, you know, or at the very least, I mean, I'm glad I included this in the document. I should have paid more attention to what I should read aloud. You know, I found myself like, wow, we're really getting into the meat here. So anyway.
Oh, thanks a lot,
Okay.
man. I thought it was
Thank
great.
thank you very much.
Cool. Well, yeah, great talking to you guys. And we'll probably have another meeting in 2 weeks, probably.
Okay, looking forward to it. And good luck with your move.
Oh, yeah, thank you. I will need it.
Yeah. Hey,
Sounds
bye.
good, Matt. Hey, I got a quick question.
Thanks, you.
Oh, yeah, yeah.
Oh, this is a little bit not so much related directly to your talk, but I'm just curious if you're probably crazy busy just putting all these things together, but I'm curious if you do any like the hackathons or anything that are out there, because there's a few coming up. I don't know if you had heard of them.
Oh, yeah. Well, you know, it's funny, like I signed up in February for that Xanadu hackathon. I didn't have time to do it, but they did send me a cool notebook that I have here.
Yeah, that was one. I was thinking of 3 of them. I was thinking of that one, and same thing with me. For whatever reason, I was just real busy that week, and yeah, it seemed like right down your alley for sure. And then yeah, there's 2 more coming up. So I just heard about the Unitary Fund is having one in May, middle of May. I just heard about that. Steve Willis sent out an email, I think this morning, about that. And then there is a like Stanford / Yale hackathon coming up as well. I got to look at the schedule. I think that's next weekend. But yeah, I mean, both of those groups, similar to the Xanadu one, you know, even if like I didn't even get a chance to dive in at all. Same thing. I signed up, didn't even dive in at all. But even just play around with the hardware a little bit would probably be cool.
Yeah, definitely. Yeah, I'll think about it. I'll definitely let you know if I end up doing this. Yeah, you know, this month is tricky, as I say, because I'm sort of committed to boxing and unboxing large amounts of things, which leave less time for quantum computing. But yeah, certainly, you know, like in May, I will be much more free.
Totally. Yeah, I got your email, so I'll send that to you just in case you're interested. Yeah, sorry, I regret. I mean, I guess you already knew about the Xanadu one, so that's good. But yeah, no, thanks again. This was awesome, and we'll see you probably in a couple weeks. And good luck with all your moving.
Cool. Yeah, thanks. Thanks for coming, Jamie. Dun-dun.